All right, welcome to the deep dive. Today we're diving into a topic that, well, it powers so much of our world, modern advances in electrical engineering.
Yeah, it's a field that's constantly evolving, constantly pushing the boundaries.
Definitely. So to get ready for this deep dive, we went through a really comprehensive review, a real deep dive ourselves. It covered all the newest breakthroughs and the challenges, the things researchers are working on. And of course, it looked at the exciting directions this whole field is heading in. Our mission, I guess you could say, is to take all that and break it down for you, to give you the key takeaways, the most significant and captivating insights, without getting bogged down in the super technical stuff.
Exactly. We're aiming to make this complex and fast-moving world of electrical engineering a bit more accessible and, well, honestly, a lot more interesting.
Yeah, that's the goal. So before we jump into the absolute cutting edge, I think it's worth taking a quick trip back in time, to appreciate how far we've come. Think back to the 19th century. Faraday's electromagnetic induction, Edison's light bulb, these were huge discoveries.
Absolutely foundational. Those discoveries really laid the groundwork for everything that followed.
Totally. But then along came Tesla with his AC systems. That was a real game changer, wouldn't you say?
Oh, absolutely. Tesla's AC system was revolutionary. Before that, Edison's DC system was limited. It just couldn't transmit electricity efficiently over long distances. But AC changed all that, and it paved the way for the power grids we still rely on today all over the world. And from there, the field just exploded. Electronics, telecommunications, computing, all built on that foundation.
It's incredible, isn't it, how that one innovation really shapes so much of what we rely on now. And the thing is, electrical engineering isn't just its own isolated thing anymore, is it? It's so interconnected with all sorts of other fields now, like computer science, for example, with AI being used in control systems, or material science, pushing the boundaries of what we can do with semiconductors.
Yeah, exactly. It's become so interdisciplinary. And you can't forget about its role in environmental studies. With the urgent need for renewable energy solutions, electrical engineering is absolutely crucial.
Totally. And what's really interesting is how central it's become to addressing some of the biggest challenges facing the planet. The UN Sustainable Development Goals, things like ensuring access to affordable and clean energy, SDG 7, or taking action on climate change, SDG 13. Well, electrical engineering is playing a really direct role in achieving those goals.
Yeah, it's not just theoretical anymore. It's having a real world impact.
Absolutely. And we see that impact across so many different areas of life. Take healthcare, for instance. We've got MRI machines, and those are lifesavers. But there's even more going on.
Oh, yeah, there's so much happening in healthcare. We're seeing these really sophisticated diagnostic tools emerging, like wearable devices that can monitor your vital signs in real time. And the accuracy is incredible, sometimes over 95%. So this continuous, precise monitoring, it's really a huge step forward for preventative medicine and for catching things early.
That's amazing. And then there's transportation, how we get around.
Oh,
Electric vehicles, or EVs as we call them. They're everywhere in the news these days, and for good reason.
yeah, the growth is projected to be massive. Back in 2023, the International Energy Agency estimated that we could have something like 145 million EVs on the road globally by 2030. That's a huge shift. And of course, it all hinges on advancements in power electronics and battery management systems, all core areas of electrical engineering. And the potential impact on CO2 emissions, it's huge. We could be talking about a reduction around 2 gigatons annually.
That's massive. And then, of course, there's how we connect with each other, telecommunications. We already have 5G networks out there. But then there are those LEO, or low Earth orbit satellite systems like Starlink, that are really changing the game.
Oh, yeah. Starlink's a great example of how electrical engineering can help to bridge the digital divide. By 2023, they already had 10 million users, and they were providing high-speed internet even to remote areas. We're talking speeds around 150 megabits per second with latency as low as 20 milliseconds. That kind of connectivity has the potential to transform access to education, healthcare, economic opportunities, all sorts of things for people in underserved communities.
It's pretty amazing to think about the impact of that. Yep. Okay, so we've already covered a lot, and it's clear that electrical engineering is a huge field. Our deep dive into the research really highlighted 7 key areas driving these innovations forward. There's power systems, renewable energy, signal processing, wireless communication, control systems, embedded systems, and circuit analysis. So we're going to delve a bit deeper into each of these, starting with power systems, the foundation of it all.
Yeah, that's a great place to start. When we talk about modern power systems, the real focus is on the shift towards what we call smart grids. It's all about making our electricity infrastructure more efficient, more reliable, more resilient. We need to be able to handle growing demands and integrate new energy sources, and smart grids are the key to that.
And we're already seeing some really interesting implementations of smart grids around the world, right? You mentioned some examples in Europe and the US.
Yeah, absolutely. In Italy, for example, Enel has this massive smart metering initiative. They've already deployed over 30 million units. What that does is allow them to monitor energy consumption in real time, which helps them manage demand much more effectively. And they're seeing results. In 2023, they reported a 15% reduction in energy waste. That's huge.
That's pretty impressive.
Yeah, it is. And then there's California. They're working on upgrading their grid with these really advanced sensors called phasor measurement units, or PMUs. These PMUs give them incredibly precise, synchronized measurements of the electrical waves on the grid. It's like taking a super high-speed snapshot of the whole power system 60 times per second. And they're combining that with AMI, or advanced metering infrastructure, which allows for two-way communication between utilities and consumers. This combination of technology is leading to a significant decrease in power outages, sometimes up to 20%. Having access to that real-time data allows them to detect and respond to disruptions much faster.
That's fascinating. It sounds like having that level of real-time information is crucial for keeping the lights on. And speaking of keeping things running, one of the most important things about a smarter grid, especially with the growth of renewables and EVs, is energy storage.
Absolutely. Energy storage is really the linchpin. It enables everything else. Right now, lithium-ion batteries are the dominant technology. They have a good balance of energy density and lifespan. We're talking about 250 watt-hours per kilogram and a lifespan of 8 to 10 years. In 2023, Bloomberg NEF estimated that they were powering about 80% of the EVs out there. But the technology is constantly improving, and we're seeing some exciting alternatives emerging.
Yeah, like solid-state batteries, right?
Yeah.
Those seem to be getting a lot of attention.
They are, and for good reason. What's so exciting about solid-state batteries is that they have the potential to really ramp up energy density and safety. Companies like Toyota have developed prototypes with an energy density of 500 watt-hours per kilogram. And because they use a solid electrolyte instead of a liquid one, they're inherently less flammable, which is a huge plus from a safety standpoint. This jump in energy density could mean that EVs could double their driving range by 2030, which would be a huge step towards mainstream adoption.
So much more energy packed into a smaller space and potentially much safer as well.
Exactly. And then there are sodium-ion batteries. Now, their energy density is a bit lower than lithium-ion, around 150 watt-hours per kilogram. But sodium is a much more abundant resource, which means the cost can be significantly lower, as much as 30% lower. That makes them really attractive for grid-scale energy storage, where weight isn't as much of a factor as cost. So different battery technologies will be ideal for different applications.
So we're essentially talking about matching the battery chemistry to the specific needs of the application.
Exactly. And it's not just about massive utility-scale storage either. We're also seeing the rise of more localized energy solutions like microgrids.
Microgrids, those sound really interesting.
Yeah, they are. They're all about making our energy systems more distributed and resilient. Think of it as taking power generation and storage down to the community level. A great example is the Brooklyn microgrid in New York City. It's a network powered by a combination of solar panels and battery storage, serving about 500 households. And it's incredibly reliable. They report a 98% uptime, which means even when the main power grid goes down, they can keep the lights on. That kind of localized resilience is going to be increasingly important, especially with the more extreme weather events we're seeing.
And that makes a lot of sense. And then, of course, we have to think about how we move large amounts of electricity across long distances. And that's where HVDC transmission lines come in.
Right. High voltage direct current transmission. It's significantly more efficient than traditional AC systems for long distance power transmission. And China's 1100 kV UHVDC project is a perfect example. It stretches over 3,000 kilometers, and they're only losing about 5% of the energy over that distance. That's amazing when you compare it to AC, which loses something like 10% or more. This kind of efficiency is essential for connecting remote renewable energy sources to the grid, like large wind farms that might be far from urban centers.
Right.
It's also really well suited for offshore wind farms, connecting them to the mainland.
So less energy wasted in transmission, which is really important as we move towards more renewable sources that might be located far away from where the power is needed.
Exactly. But there's a flip side to all this interconnectedness and digital technology: cybersecurity. As our power systems become more reliant on digital systems, they also become more vulnerable to attack. And the 2015 cyber attack on the Ukrainian power grid was a wake-up call. It left hundreds of thousands of people without power. IBM reported in 2023 that smart grids are facing an average of 1.4 million cyber threats every single day. So securing this infrastructure is absolutely crucial.
1.4 million threats per day. That's a sobering thought.
It is. It highlights how crucial robust cybersecurity measures are for protecting our power systems.
Definitely. So what about the future of power systems? What are some of the key areas of development that researchers are working on?
Well, there's a lot going on, but one really exciting area is the use of AI for predictive maintenance. We're seeing neural networks that can analyze all sorts of data from grid components and predict when equipment might fail. Some systems are already achieving around 90% accuracy in detecting potential faults. This means we can be proactive about maintenance, preventing outages before they happen. That's huge for reliability.
That's pretty amazing.
It is. And we're also seeing a push towards self-healing grids. These grids can automatically detect and isolate faults, rerouting power to minimize disruptions. And of course, energy storage technology is constantly improving. We're looking at things like flow batteries, which have the potential to last for 20 years or more. They could be ideal for long-duration grid storage. Ultimately, building more sustainable, reliable, and secure power systems is going to require collaboration across many different disciplines. We need engineers, cybersecurity experts, policymakers, everyone working together.
Okay, so we've covered power systems. Let's move on to another really important area, renewable energy. It's at the forefront of the fight against climate change, and it's really exciting to see the progress being made. We've talked about solar and wind, but of course there's also hydropower and geothermal.
Right. These are all key players in the shift to a cleaner energy future, and solar technology in particular continues to make impressive strides. Perovskite solar cells, for example, are reaching efficiencies of around 25% in the lab. That's already surpassing the typical efficiency of silicon-based solar cells, which are usually around 15 to 20%. And perovskites have the potential to be manufactured at a much lower cost. They're also very flexible, which opens up all sorts of new possibilities. But there's a challenge: stability. Data from the National Renewable Energy Laboratory in 2023 showed that they can degrade about 50% faster than silicon cells under humid conditions. So making them more durable is a key focus for researchers.
So there's a lot of potential, but they need to be made more resilient for real-world use.
Exactly.
What about wind power? We're seeing some incredibly large turbines being built these days.
Oh, yeah. GE's Haliade-X turbine is a great example. It has a 220-meter rotor that's massive, and it can generate 15 megawatts of power. That's enough to power something like 16,000 homes. And there's a real trend towards offshore wind farms. Wind speeds over the ocean are generally higher and more consistent, which means you get more reliable energy production. We're talking about average speeds of 10 meters per second, double what you typically see on land. So that's a big advantage.
That makes sense. And with all these different renewable sources coming online, we need ways to manage them effectively, especially since their output can fluctuate depending on the weather.
Exactly. That's where energy management systems, or EMS, come in. They're all about optimizing the integration of renewables into the grid. A good example is Denmark, a country that's really leading the way with solar and wind power. They use sophisticated AI algorithms to forecast energy output with amazing accuracy, something like 95% according to the International Renewable Energy Agency in 2024. That accurate forecasting allows them to balance supply and demand in real time.
So it's about using AI to predict how much power will be available from these variable sources.
Right. And then there's hydropower. Pump storage hydropower, in particular, is like a giant battery for the grid. Switzerland has a huge pump storage network, about 20 gigawatts, and they can store excess energy generated from other sources like solar and wind. It works by pumping water uphill when there's excess energy, and then releasing it to generate electricity when demand is high or renewable output is low. It's about 85% efficient. And while we haven't talked about it in detail, geothermal energy is another important player. It's a consistent and reliable renewable energy source in certain locations.
And we're seeing more and more hybrid systems popping up, combining different renewable sources and energy storage to create a more reliable and consistent power supply.
Definitely. Hybrid systems are becoming increasingly important. Spain's Gemma solar plant is a great example. It combines concentrated solar power with molten salt energy storage. This allows them to generate electricity around the clock, even when the sun isn't shining, enough to power about 25,000 homes. And then there's the Lake Turkana wind power project in Kenya, a 310 megawatt wind farm that's providing power to about 1 million people in a region that previously had very limited access to electricity. So hybrid systems can really make a difference.
These examples really highlight the potential of renewables. But, as we touched on earlier, intermittency is a challenge. The output of solar and wind power can fluctuate quite a bit depending on the weather.
Yeah, it's a key challenge that we need to address. Solar power output can drop by as much as 70% on cloudy days, and wind, well, it's inherently variable. The National Renewable Energy Laboratory released data in 2023 showing just how significant these fluctuations can be. That's why energy storage and accurate forecasting are so critical. And research in these areas is moving forward rapidly. We're looking at tandem solar cells, which combine perovskite and silicon layers. They have the potential to reach efficiencies of over 30%. And AI-driven energy management systems are getting more and more sophisticated, optimizing grid operations in real time. There's also a lot of potential in ocean energy, like tidal power. The global potential there is estimated to be around 500 gigawatts. And if we can successfully scale up these hybrid renewable energy systems globally, the International Energy Agency believes we could see a 5 gigaton reduction in annual CO2 emissions by 2040. That's massive.
It is. It really shows the potential for a cleaner energy future. Okay, let's shift gears now and talk about signal processing. Now, this might sound a bit technical, but it's actually behind so many technologies we use every single day.
Absolutely. Signal processing is everywhere. It's all about analyzing and manipulating signals, whether it's audio, images, or data from sensors.
So it's about making sense of the information that surrounds us.
Exactly. One really important technique in signal processing is adaptive filtering. It uses algorithms like the least mean squares, or LMS algorithm, to automatically adjust a filter to remove unwanted noise or interference. Think of noise-canceling headphones. They use adaptive filtering to block out background noise. And high-end hearing aids, like the ones Bose makes, they often use the LMS algorithm to reduce background noise by as much as 30 decibels, making speech much clearer for the wearer.
That's a great example of how signal processing has a direct impact on people's lives. And then there's the use of convolutional neural networks, or CNNs, in medical imaging.
Right, CNNs. They've really revolutionized medical diagnostics. They're a type of AI that's particularly good at analyzing images, like MRI scans. They work by processing images through multiple layers that learn to identify specific features, and they can be incredibly accurate. Some CNNs are achieving 98% accuracy in detecting tumors in medical images. But there's a trade-off. Training these sophisticated networks requires massive data sets, often over 1 million images, and a lot of computational power on the order of 10 teraflops.
So it's a balancing act between achieving high accuracy and managing the computational resources required. And then there's the whole world of quantum signal processing, which sounds pretty mind-blowing.
It is. It's a field that's exploring how the principles of quantum mechanics, things like superposition and entanglement, can be applied to signal processing. And the potential is huge. We could see exponential speed-ups in certain tasks like Fourier transforms, which are fundamental in signal processing. This could have a big impact on cryptography, potentially doubling the speed of encryption and decryption.
So we're talking about a fundamental shift in how we process information.
Exactly. And on the hardware side, companies like Texas Instruments are developing incredible digital signal processors, or DSPs. Their C6000 series, for example, can perform tens of billions of operations per second. These chips are essential for real-time signal analysis in applications like autonomous vehicles and 5G networks. And we're even seeing examples in telemedicine where traditional DSP techniques are being combined with machine learning to improve things like ECG signal denoising. They've seen accuracy improvements of up to 95%. So it's a really exciting convergence of old and new techniques.
It sounds like it. What about the challenges in signal processing? What are some of the things researchers are grappling with?
Well, energy efficiency is a big one, especially for complex AI models like CNNs. NVIDIA reported in 2023 that training some of these deep neural networks can use a lot of power, as much as 500 watts. And while quantum processing has the potential to be incredibly fast and efficient for certain tasks, we're still limited by the availability of stable and scalable quantum hardware. Current quantum computers only have a handful of qubits, usually less than 100. And future research is focusing on using FPGAs or field programmable gate arrays to accelerate signal processing, potentially reducing latency by as much as 40%, and on developing more efficient quantum algorithms that can be implemented on near-term quantum hardware for things like remote sensing.
It sounds like there's a lot of work still to be done.
There is, but it's a rapidly evolving field.
Okay, let's move on to another area that's seen some incredible advancements. Wireless communication. From the early days of radio to the 5G networks we have now, it's been an amazing journey. And now we're on the verge of 6G.
Yeah, 5G has been a huge leap forward, and 6G promises even more. A key innovation behind 5G is massive MIMO, or multiple input, multiple output. It uses base stations with a large number of antennas, sometimes 128 or more, and techniques like beamforming, which allows the base station to focus radio signals directly at individual users. This means much faster data rates, potentially reaching 10 gigabits per second, and much higher spectral efficiency. 5G can support about 3 times as many devices within the same amount of spectrum as 4G, up to 1 million devices per square kilometer. And 6G is looking to push things even further by using the terahertz frequency bands. Those frequencies are between 0.1 and 10 terahertz, and they have the potential to deliver speeds as high as 100 gigabits per second. But there's a challenge. Terahertz waves have a limited range, maybe only around 100 meters. So to really make 6G work, we'll need a much denser network of base stations.
It's much faster speeds, but over shorter distances. It's a trade-off.
It is. And we can't forget about LEO satellite networks like Starlink, which are also expanding our wireless communication capabilities in a big way.
Right, Starlink. They have a constellation of over 4,000 satellites in low Earth orbit, providing internet access to people all over the world, including remote areas. As we talked about earlier, they're already delivering speeds of around 150 megabits per second with latency around 20 milliseconds. And by 2023, they had 10 million users. That's incredible growth.
It is. And another important trend is the rise of edge computing. This involves processing data closer to where it's generated rather than sending it all the way to the cloud. It can reduce latency significantly, sometimes by as much as 50%, which is crucial for real-time applications like autonomous driving. And South Korea, with its early and extensive rollout of 5G, is a good example of what's possible. They've achieved 90% urban coverage and very low latency, around 1 millisecond in some areas. That kind of performance is going to be essential for things like smart factories and other industrial applications.
Ultra-low latency is going to be key for so many emerging technologies. But with all these advances come new challenges. And cybersecurity is one of the biggest. Just like with power grids, the more complex and interconnected our wireless networks become, the more vulnerable they are to attack.
Exactly. And 5G, with its increased complexity and massive number of connected devices, is a prime target. Nokia reported in 2023 that they were seeing about 200,000 cyber attacks targeting 5G networks every month. That's a lot. And then there's the issue of spectrum congestion, especially in urban areas where demand for wireless bandwidth is so high. The Federal Communications Commission predicted in 2024 that we could see 80% saturation of the available 5G spectrum in some major cities. So we need to find ways to use the spectrum more efficiently.
It sounds like there's some big challenges to tackle.
There are. And researchers are focusing on things like AI-driven dynamic spectrum sharing, which could increase efficiency by around 25%. They're also working on pushing the boundaries of terahertz technology to overcome those range limitations for 6G, and they're developing more energy-efficient communication protocols. So there's a lot of innovation happening.
Okay, let's move on to another really interesting area, control systems. This is the field that's really driving automation and enabling autonomous operation across so many industries.
Absolutely. Control systems are fundamental to how we automate processes and create intelligent systems.
So they're the brains behind the machine, so to speak.
Yeah. In a way, yes. One very common and powerful technique is model predictive control, or MPC. It's a way for a system to make decisions by predicting its future behavior over a short period and then optimizing its actions to achieve a desired outcome. For example, in HVAC systems, MPC can be used to minimize energy consumption while maintaining a comfortable temperature. It can lead to energy savings of around 20%.
Yeah.
And in autonomous vehicles, sensor fusion, which combines data from multiple sensors like LiDAR, radar, and cameras using algorithms like Kalman filters, is essential for accurate and reliable navigation. Waymo reported achieving 99% accuracy in their autonomous driving systems using these techniques in 2023.
So we're talking about optimizing things like climate control and enabling cars to drive themselves.
Exactly. And then there are collaborative robots, or cobots. These are robots designed to work safely alongside humans, and we're seeing them being adopted more and more in manufacturing, especially in automotive assembly. The International Federation of Robotics reported in 2024 that cobots now make up about 30% of the robots deployed in that industry. They have to adhere to strict safety standards like ISOTS 150.066 to ensure they can work safely with people.
That's really interesting. So it's not just about replacing humans with robots. It's about finding ways for them to work together effectively.
Right, and we're seeing some impressive applications of control systems in fully autonomous systems like Tesla's autopilot. They use model predictive control to manage various aspects of the car's operation, and they've reported a 40% reduction in the rate of collisions in vehicles using autopilot. And then there's the whole area of multi-agent systems, where multiple independent agents, like a swarm of drones, can coordinate their actions to perform complex tasks. These systems use decentralized control algorithms, meaning there's no central command center, and they can achieve efficiencies of up to 95%.
That's incredible.
Yeah.
So much coordinated behavior without a central brain.
It is. And some of the big challenges in this field are ensuring that control systems are robust against unexpected disturbances and effectively coordinating the actions of large numbers of agents in these multi-agent systems. Researchers are looking at bio-inspired control strategies, studying how animals like flocks of birds coordinate their movements to develop more resilient and efficient decentralized control systems. It's a really fascinating area of research.
It sounds like it. Okay, let's talk about embedded systems. These are the little computer systems that are embedded in so many devices we use every day. Our smartphones, our smartwatches, our appliances, even industrial machinery. They're really the driving force behind the Internet of Things.
Exactly. Embedded systems are everywhere. They're the intelligence within all these connected devices. And a key consideration in their design is energy efficiency. Many of these devices run on batteries, so they need to be as power efficient as possible. Processors like the ARM Cortex and Cerum Curies are designed specifically for low-power applications, and you'll find them in billions of devices globally. And wireless communication is essential for IoT devices. Technologies like Bluetooth Low Energy, or BLE, and Zigbee are commonly used for connecting low-power devices, and we're seeing the emergence of Wi-Fi 6E, which could reduce network congestion by about 25% in dense IoT environments.
So connecting all these devices in a way that's both efficient and reliable.
Right. And security is paramount. We've seen a rise in large-scale cyber attacks that exploit vulnerabilities in IoT devices to create botnets. There was a notable attack in 2022 that affected over 1 million devices. So using robust encryption, like AES-128, is essential for protecting the data these devices collect and transmit. Think about a Fitbit, for example. It can collect something like 100,000 data points from a user every day, and it typically has a 99% uptime. And as 5G networks become more widespread, the processing demands on these little embedded systems are going to increase dramatically, probably tenfold. So we need to make sure they're not only energy efficient and secure, but also powerful enough to handle the growing workload.
So it's a constant balancing act between those different requirements.
It is. And some of the key challenges for the future of embedded systems are real-time processing and security in 5G ecosystems. Researchers are exploring the use of blockchain technology for device authentication and secure data management. They believe it could reduce security breaches by as much as 50%.
That's a big improvement. Okay, last but certainly not least, let's talk about circuit analysis. This is the foundation of electrical engineering, the design and analysis of the electronic circuits that make all these technologies possible.
Absolutely. Circuit analysis is where it all begins. And we're seeing continuous advancements in transistor technology. Intel, for example, announced 2-nanometer transistors in 2023. These tiny transistors can deliver a 40% performance boost compared to previous generations. And we're also seeing a move towards 3D integrated circuits, or 3D ICs, which involves stacking multiple layers of silicon chips on top of each other. This allows for more compact and energy-efficient designs, and tools like SPICE-E, which are used for simulating electronic circuits, are essential for designing high-frequency printed circuit boards, or PCBs, used in things like 5G. They help engineers ensure signal integrity at those high speeds. But as circuits become more densely packed and operate at higher speeds, heat becomes a major issue. Integrated circuits can exceed 100 degrees Celsius under heavy load, so thermal management is a big challenge. And then there's the development of quantum circuits, which use qubits as their building blocks. These circuits have the potential to deliver exponential increases in computational power for certain types of problems. But the challenge is that qubits are very delicate. Their quantum state can be easily disrupted, and current coherence times are very short, less than a millisecond.
So managing heat and making sure these qubits stay stable are major hurdles.
They are. And researchers are working on things like microfluidic cooling to dissipate heat more effectively, and superconducting quantum circuits, which could potentially offer much longer coherence times for qubits. So there's a lot of exciting research happening.
Sounds like it. Wow, this has been a fascinating deep dive into the world of electrical engineering. It's amazing to see how all these different areas are interconnected and how they're all contributing to solving some of the biggest challenges we face. From smarter power grids and renewable energy to signal processing, wireless communication, control systems, embedded systems, and circuit design, it's all connected.
It is, and what's really exciting is the potential for all these innovations to drive us towards a more sustainable future, to create economic growth, and to improve people's lives. The International Energy Agency's projections of a 10 gigaton reduction in CO2 emissions by 2050 from EVs and renewables is a testament to that potential.
It's a powerful reminder of what's possible. But, as we've discussed, there are still challenges. Cybersecurity is a big one, making sure our increasingly interconnected systems are secure, and energy storage is another one. We need to find ways to scale up energy storage solutions to really unlock the potential of renewables. It's clear that solving these complex problems is going to require collaboration across many disciplines, bringing together engineers, scientists, policymakers, and even ethicists.
Absolutely. We need to invest in research and development, strengthen education programs to train the next generation of engineers, and foster collaboration between academia, industry, and government. It's going to take a concerted effort to keep pushing the boundaries in this field and ensure a future that's both technologically advanced and sustainable.
Well said. And on that note, here's a final thought for our listeners to ponder. As we continue to develop and implement these increasingly sophisticated and autonomous systems, powered by all these advancements in electrical engineering, what are the broader societal shifts and implications that we need to be prepared for? What kind of future are we shaping? Thanks for joining us for this deep dive. It's been a pleasure.
My pleasure.
Until next time.
See you then.